This is my first video, first actual video. You might see some of my other videos, but this is my first math video. So USAMTS recently ended, still waiting for prizes, but I think they're coming out in this near future. So this was year 35. I'm going to be talking about one of my favorite problems in the contest because it was challenging for me, but eventually I solved it. Don't take mine as the most efficient solution, but it, in my opinion, still a decent solution, and it teaches you about really important configuration in Olympiad geometry. So the problem reads: the incircle of triangle ABC with AB not equal to AC has center I. Okay, so this is the incenter, and is tangent to BC, CA, and AB at D, E, and F respectively. So you see, if it's tangent, it's a 90-degree angle. It might be used later. Okay, so the circumcircle of triangle ADI intersects AB again at AC and XY. So we're extending the sides and prove that EF bisects XY. So you want to prove where EF, let's call it M, hits the line XY. That's the midpoint of that segment. So don't worry if this seems a lot to handle. I have a diagram set up with GeoGebra. It's called USAMTS right here. Let's go. So we have, first of all, let's go step by step. Let's make this a little more usable triangle. So what GeoGebra is really good for, it shows you all the configurations, but you can't really use it as a formal proof. I kind of got docked on one question this year, because this is my first year actually learning how to write proofs. But but this is a good tool to help you notice stuff. So we have triangle ABC, as you saw in the question, triangle ABC, and it has an incenter of I right here, because it said the incircle has center I, and it says it's tangent to BC, CA, and AB at D, E, and F respectively. So tangent means a 90-degree angle. So that means you're drawing a perpendicular line from I to BC and etc. for all of them. So these are the feet of the incircle. So not the feet of the incircle, the tangent points of the incircle, but you're drawing altitude from like I. So you can see these should be all right angles: IFB, IDB, IEC. So now we extended the lines, I'm pretty sure, yeah. So the circumcircle of ADI, so this is the triangle ADI. If you extend the lines AC and AB respectively, it hits Y and X, right? So yeah, if you see AC extends to hit Y, so the circumcircle is the circle that can be surrounded triangle completely. So it can go like, it has to go through all three of the vertices. So this goes AID, this is the circumcircle. It's a kind of obtuse triangle, that's why it's such a big circumcircle. So this is the point Y, this is the point X. So basically what we want to prove that is EF bisects XY. So right, what we called here is line EF hits the line XY at the point M. So we want to prove that this segment, let's see, where do we have the pen? Okay, so we want to prove that this segment equals this segment. So this kind of, yeah, this letter naming is foreshadowing. We're going to prove that this is the midpoint, but yeah. Okay, so I do have my full proof here. It was a little bit fun. I wrote trivially to make me sound like an Olympiad mathematician, but yeah, this is my USAMTS proof. So I even linked my diagram that was right here. So we're applying the Menelaus theorem. So how do we know this, right? So we have two main triangles, right? We have ABC, AID, right? So ABC, they're kind of giving you everything, and what we want to solve, everything here is on this side. And AID is also not really useful as per se, at least in this solution, right? But we have good points here, X and Y. and A is kind of the central point, right? So you can go through the triangles, but the big triangles you see is because A and I are the pretty big points. C is just here in the corner. So yeah, so we have, and then M obviously is the biggest point in this. So we can try triangles AYX, I think, and then YIX. So what do you want to know, get per se, is probably named points. So if you can have a named point configuration, mostly like if look here, you have AYX, right? And you can see you have this line going through the triangle. So this is similar to a Menelaus configuration, right? So because it's similar to the Menelaus configuration, you want to notice these things. So like you can also see a Menelaus like configuration right here, YIX, and it goes through M, this line, but this point right here is not named, right? But if you notice on this triangle AYX, this point is named right here. So that's why you want to use this configuration, AYX with ME. So basically you had to do a lot of practice problems to notice these configurations, but eventually you get it, right? So it took me a pretty long time to notice it, so don't worry about it if you can't notice it immediately. So you see AYX, we realize that one of these AYX or IYX have to be the focus triangles to help us solve the problem, preferably. And then we see this Menelaus configuration, right? We have this line, and all three of these points line up nicely, right? YA, basically the Menelaus states that if we have a line passing through a triangle, right? Let's draw this. Yeah, that's definitely a triangle, guys. Okay, so we have this, right? Like either two points lie on the triangle and one point lies on the extension of the side. Okay, why can I not draw a dashed line? Or all 3 points just lie on the extension of the side. That I can't immediately think of how to draw that. But oh yeah. So if you have some, oh my god, you have something like this, right? And then you have like a line like that. So you have this lies on this extension, this lies on this extension, and this lies on that extension, right? Something like that. So it gives you a sequence of ratios: xm over my times ye over ea times af over fx. A good way to remember this is this alternating letter sequence: m over m, e over e, f over f. And then they also have to go in logical order: xm or ym, ye or ae, and then something like that. So basically it states that this ratio has to be 1. But what we want to prove, and based on the question, is, let's see, EF bisects XY. So we want to prove this is the midpoint M, right? So that means XM over MY. So if that is true, XM over MY equals 1 then. So then that means this ratio must equal 1 in that case. But also, I use my favorite word trivially here. What am I saying? AF and AE are both equal because they both are tangent to the incircle, right? And tangent lines that originate from the same point to the same circle are equal. So that's how we get this cancellation. AF and AE both are equal, so they cancel out. So basically all we need to prove is YE over FX equals 1. And if two things divide each other to get 1, that just means they both equal each other. So YE equals FX is all we need to prove. But look here, like YE over FX is a kind of random set of points, right? YE is right here, and then FX is also kind of, ooh, straight lines, guys. But YE and FX are kind of random points, right? So what you want to notice, right, is you we have triangles with these. So triangles and circles are very important in Olympiad Geo. So right, you can look at triangles. Oh, and we should have labeled these angles earlier, right? The 90 degrees. Sorry, I forgot. But right. So we see this forms a very convenient triangle, right? So this and this line, which we have, and this, right, both form a right triangle, if you see. And if you see, this is the in radius and that's also the in radius, and the radii of the same circle are equal. So that means in the case where xf and ye are equal, then yi and ix also have to be equal, because Pythagorean theorem, right? So if ye squared plus ei squared equals yi equals, and then xf squared plus if squared has to equal ix, and these both have to be equal to each other because they have the same side lengths. And this is just side angle side congruence, right? Because it's two legs and the 90 degree angle, right? Yeah. So that means our whole problem was kind of complicated at first. It said prove that EF bisects XY, and it's like kind of random, right? But it all reduced down to YI equals IX. So all we need to prove now is YXI is an isosceles triangle. And there's multiple ways we can do this, but one of the easiest ways to prove that something's isosceles is that this equals this, right? So basically the two angles are equal. So how can we do that? So let's call this angle, which is the only unique angle here in that triangle, x. Then we just need to prove that this is 90 minus x over 2 and this is 90 minus x over 2. So let's see what we can do here. How about let's clear up this space a bit. And yeah, so we have this as x. So if we get, this is x, right? There's an inscribed angle theorem. Inscribed angle theorem states any angles that have like angles like this, right? So these points all lie on the edge of the circle, the circumference of the circle, and they have two of the points as the same. And then the angle, the inscribed arc basically is the same, and they lie on the edge of the circle. Then these angles must be equal. So that's the same for this, YIX and YAX. So basically we're left to prove, that means we get this is also equal to x based on this circumcircle, because we have this arc YX, major arc YX. So then if this is x, since this is a straight line because they told us this was the extension of the line, this is 180 minus x. And since that, and based on that, we also know, let's check right here, what we did, yeah, right here. So since AI is the angle bisector, wait, I should probably, can I zoom in? Yes, I can. So we drew AI here earlier, right? AI helps define, so basically the in-center is the intersection of all three angle bisectors of the circle. I use this to draw, help draw my diagram, because I don't know if there's an in-center function, but look, BI, CI, and these basically angle bisector means the line that divides this whole angle into two equal parts, right? So basically that means that this part of this whole angle and this part of the whole angle are equal. So we said this whole thing, right? This whole thing is 180 minus x. So half of that must be 90 minus x over 2, right? So if that's 90 minus x over 2, right? We can use the same inscribed angle. But now, this might be kind of hard to see, so we're going to zoom in. You see how this is BAI is 90 minus x over 2. I should have drawn this better. Okay. Okay. BAI is 90 minus x over 2. So, because of the same inscribed angle thing, BAI is the same as XAI. And XAI is arc XI. And that has another angle right here, XYI. And do you notice something about XYI? It's part of the same triangle we were looking at. And we just proved that that equals to 90 minus x over 2. And if that equals 90 minus x over 2, this also has to equal 90 minus x over 2. And that proves that this angle is equal to that angle, and thus this is an isosceles triangle. Yi equals Ix, and that means this. And since we proved that, our whole thing simplified to that, if you remember. So that means M must be the midpoint of xy, because all these other things fall through. So the main thing to notice here was the configuration. If you notice what was the most important triangle here and how you can configure it, guys, this very straight lines, but you get the point. So if you notice this configuration, oh, this is a wrong triangle, my bad. So yeah, if you notice that configuration, right, you notice the Menelaus configuration, which comes with practice, everything else falls through, and you just want to keep trying to simplify the problem. So yeah, that's it for today. And guys, thanks for listening to my first video. Good luck in your math journey. Thank you.